what we have is you start with a basic box, and you have circles, that overlap. Okay. And this circle represents quadrilaterals. I made that way too small, didn't I? So this circle represents quadrilaterals, and this circle represents convex figures. And the whole box is, your world of polygons. And you have quadrilaterals and you have convex figures. And a rectangle is both. So he lives in the overlap.
R means both?
R
means both?
No, rectangle.
Oh.
I can't write rectangle in there. So we have all the quadrilaterals in this circle. This is the circle where all the quadrilaterals live. So you've got parallelograms and squares and trapezoids and just whatever. And over here you have all the convex polygons. And more than just rectangles are going to fit in here, because parallelograms are convex and trapezoids are convex and stuff. But for sure, rectangles are both quadrilaterals and convex. So if they live in the overlap, it's a conjunction. Okay. If you have disjunction, we have the world of polygons again. So big, giant box of polygons. And we have quadrilaterals, and we have convex. Wow, that's not a very good picture. So I'm going to do Q for quadrilaterals. No, I guess it's P. P for quadrilaterals and Q for convex because of here, just to have the space. Okay, and then we have our statements. A figure is a quadrilateral, a figure is convex. Oh, this would be P and Q for rectangles. So we have a figure is a quadrilateral, a figure is convex, or a figure is one or the other. Okay. So what we have is in the quadrilateral area over here, we have the ones that are not convex. And in the convex area over here, we have the non-quadrilaterals. So these are all quadrilaterals that are not convex. These are all convex figures that are not quadrilaterals. And in the middle, you have the things that are both. Yes, those would live outside the circle. So for example, hexagons. Nope, those are convex. Concave stars. Stars are concave and they're not quadrilateral, so they are polygons, so stars are out here in the outside of the circles. Okay, so what we have here is anything that is a quadrilateral but is not convex. On this side we have anything that is convex but is not a quadrilateral, and only the overlap is when you have both. That's how Venn diagrams work. We have the number of people who can or cannot attend the May or the June Spanish Club meetings. So this represents May. This represents June. Okay. So how many people can attend the May or the June meeting? This is and. We've got 5 plus that 6 can go to May, right? That's 11 that can go to May. And then the same 6 can also go to June. So we have 11 and 14 can go to either or. So it's going to be 25. 25 people can go to either. If we say how many people can attend the May and the June, that's only the overlap. So that's 6. Okay. If we ask for just May, that's 11. If you ask for just June, that's 20. Do you see how that works? And then how many people can't attend either meeting? 2, right? Because those are the people that are not inside the circles. Okay, if we go to the next one, we have prom attendance, junior prom, senior prom. So how many, and these are for graduates, so how many people attended their senior but not their junior? So these are your senior prom. These are your junior prom. This is the area of people that did both. Yeah, so 25. How many people attended both? How many didn't attend either one? And then how many students graduated last year? We're going to add all of those up because these are all of the graduates who did or did not attend junior and senior prom. So we add up everybody. Is it? Actually, I'm going to do 37 next. Then I get a 10, then I get a 6, then I get a 1, and then I'm going to do 85.
Just do 110.
I could. 270. So 270 graduates. The 85 plus 123 attended junior prom. The 25 plus 123 attended senior prom. 123 did both. And 37 said, I don't care for dances, thank you very much. So conditional statements are cause and effect. And they do also have truth values. An example, I use this one a lot with my child. If you clean your room, then you can play video games. The idea is if he does not clean his room, then he does not get to play video games, right? So it's conditional. The first condition is you clean your room in order to get the result of you play video games. It's written in the form of an if-then statement, and it is if P, then Q. So when we had a rectangle is a quadrilateral, a rectangle is convex. You could say if a rectangle is a quadrilateral, then it is convex, kind of thing. So it's another kind of conjunction of or compound sentence, but it's an if-then compound sentence instead of just an and or. It's conditional. So to symbolize it, we do P arrow Q. And this is read P implies Q. And the implication is that if P happens, then Q will happen. Okay, so that's why P implies Q. So you can read it as if P then Q or P implies Q. Okay, the hypothesis is the phrase after if. Whoops, phrase is RA, not H. This is the P part. In my example sentence, the hypothesis is you clean your room. Okay, that's the hypothesis. The hypothesis is that the room is cleaned. The conclusion is right after the then part. That's the Q. So in my example, the conclusion would be you can play video games. Okay, so if you clean your room, then you can play video games. This is an if P then Q. Hypothesis, you clean your room. Conclusion, you can play video games. Some hypotheses and conclusions. It's very easy if it's already in the if-then format. I just say, okay, hypothesis. And then I say, okay, conclusion. Sometimes we don't speak that way though. I tell my son, if you clean your room, then you can play video games. I don't actually say that. What I say is, you can play video games if you clean your room. That's the way we actually speak, right? I mean,
My parents say that
oh well. So sometimes they're backwards. Look for the if. Okay. This is my hypothesis, which makes this my conclusion. Because I could rephrase that: if a number's last digit is 0, then it is divisible by 10. So you're going to look for the if. The if is the really important thing to try to find. What comes after the if is the hypothesis. The rest of it's the conclusion. So if it's backwards or out of order. Okay. If a polygon has 6 sides, then it's a hexagon. So a polygon has 6 sides is the hypothesis. It is a hexagon is the conclusion. Okay, where are we now? Where's my hypothesis? And then conclusion. Now, if we were to rewrite the hypothesis and conclusion, we wouldn't write the first one is sold out. We would write if the first performance is sold out to make it more, to make it make sense, right?
Well, if you put a column after sold out or after the word out, it would be almost sense. It would make sense.
Not really. If we were just saying what's the hypothesis would be the first performance is sold out. Then the conclusion would be another performance will be scheduled. So we'd have to have a subject in there. So if you are actually rewriting the hypothesis, you'd put the word performance in. Just like up here, we put the last digit, a number's last digit is 0. Then kind of thing. Have conditional statements that are not including the word if and then, and you need to be able to recognize those. Conditional statements are statements that contain a condition in them. So something that has to be done in order for something else to happen. So points will be deducted from any paper turned in after Wednesday's deadline. This is the condition that would have to be met in order for the points to be deducted. So it can be in a negative condition, right? Like something you don't want to happen. But so if you look at this, points will be deducted from any paper turned in after Wednesday's deadline. The thing that has to happen for the points to be deducted is that the paper's turned in late. So that's the if part. That's the hypothesis. Then points will be deducted. That's the conclusion. That's what will happen if the other. This is what will happen to you if the first thing happens. Okay, so a mammal is a warm-blooded animal. There's a couple of ways that you could write this one, actually. So I could say if an animal is a mammal, then it is warm-blooded. Or I could say if an animal is warm-blooded, then it is a mammal. Is that true?
Yes.
This one for sure true, yeah? Is this one true?
No.
Yeah, because we have other animals like dolphins and stuff that are mammals, but not warm-blooded.
Yeah, and it's also warm-blooded. But what about birds?
That's what I'm saying.
What about birds?
Yeah, it is.
Guys, what about birds?
Marsupials.
Birds are warm-blooded, not a mammal, right? So if you are looking at this, this is true. This is true. This is not necessarily true. So don't use this one. Does that make sense? So if you can't know, if you don't know which one is the condition for the other one, write them out and then think about, is this always true? This is for sure always true. So is this one always true? Not necessarily, because there's other warm-blooded animals other than mammals. There are some warm-blooded fish. There are warm-blooded birds. Not lizards, but you know, I mean. A prism with bases that are regular polygons is a regular prism. Which is the condition? Like, what do you have to these to be the other? You have to have regular polygons to be a regular prism, right? So you could say, if a prism has bases that are regular polygons, then it is a regular prism. We've got the dollar bill thing. 4 quarters can be exchanged for a dollar bill. Then you can exchange it for a dollar bill. Yeah, that works. Okay, and then the sum of the measures of two supplementary angles is 180. Your sum has to be 180 in order for you to be supplementary. So I'd say if your sum is 180, then your angles are supplementary. I'm not going to write that right this second. What I'd like you to do